Hi guys, can you guys hear me?
Yes.
Okay. All right. So the first homework, chapter 14 homework, is going to be due this Sunday, 11:59 p.m. So make sure you guys finish your homework before the due date. And if you're still seeing discrepancy between your homework on the actual Achieve Macmillan website and Web Campus, please wait until the due date is passed. If you still see the discrepancy after the due date, you can send me a screenshot of your scores and send it to my email, and I will contact the Macmillan Achieve representative. But once the due date is passed, you should not be seeing the discrepancy anymore. Okay. I would like to quickly make a little correction for sample exercise 14.15 that we solved on Tuesday. So what I did was K1 and K4 reaction for step 1, and then reverse reaction for step 2. Step 1, the rate constant for those would cancel out and equal to 1. But then if I do that, I will be left with K2. So I was going back to this problem after lecture, and it didn't really make sense to me, because then you would be left with K2. K2 is a rate constant for step 2 of the reaction. Rate constant for step 2 of the reaction, that shouldn't be the overall rate constant for the entire reaction. Okay, so I went back again and then I read, and I made a mistake. So the rate of the forward reaction will definitely equal to the rate of the reverse reaction in the equilibrium reaction. However, the rate constant for the forward reaction and rate constant for the reverse reaction, it can be 1. It can cancel each other if they're same equal value, but that is not always the case. So if we cancel this out, that will be a very misleading. Okay, so I want to make a correction to what I stated. This K1 and K negative 1 means rate constant for forward reaction for step 1 and rate constant for reverse reaction for step 1. They do not cancel out. We will leave it there. The overall rate constant for entire reaction, for overall reaction, is multiplication of all the rate constants combined together. So this is going to be the combined rate constant. Okay, so in the future when you're solving this kind of problem, do not cancel this portion out. Just leave everything. If you have step 1 and step 2, if step 1 is in equilibrium, you will have forward reaction rate constant and reverse reaction rate constant. Keep those. Okay, so your overall rate constant is going to be step 2 rate constant multiplied by step 1 forward reaction rate constant divided by reverse reaction rate constant. That is overall rate constant. Okay, so I know that you guys were having a lot of trouble with this type of exercise, so I'm going to go over some of the homework problems. Okay, I'm pretty sure a lot of you guys have finished the homework already, but if you haven't finished this portion, I will go over the detail, and it will help you to complete the homework faster with better understanding. So And I'm not going to post this on Web Campus because this is going to be the answer key for your homework problem. So if you want, you can take a note or yeah. So let's take a look at this reaction mechanism where you have step 1 is 2A going to producing product B. Step 2 is reactant B plus C producing product D. Okay, they already told us that step 1 is the slow reaction. Okay, again, slow reaction is going to be the rate determining step. So your overall rate, reaction rate is going to be determined by this, governed by this slow reaction. Okay, that's what we know from chapter 14. So the question is asking us to determine the rate law for the overall reaction. Again, overall rate law is going to be the rate law from slow reaction, which is a step 1. Okay, so before that, we want to um, determine the intermediates in the reaction. Okay, I didn't do that for chapter 14 during the lecture, and a lot of you guys are confused. So I'm just going to show you how to find intermediate for all of these homework problems. Okay, so in order to find the intermediates, what we're going to do is we're going to add up all the reactants and add up all the products. Okay, so if you add up all the reactants, you have 2A plus B plus C. And then for the product side, you will have B and D. Because B appears on both reactant side and product side, B is being consumed, B is being produced, and then it's being consumed again. This is an intermediate. So B is intermediate. Okay. And now we're going to express our rate law. The rate law is going to be, the rate law of overall reaction is going to be the rate law of the slow reaction. So that is going to be rate constant of step 1 multiplied by concentration of uh, the reactant, which is A, raised to the second power because you have 2 moles of A. Okay? So you always want to check when you're dealing with multi-step mechanism, you always want to check and see if your rate law contains intermediate or not. Okay, if it contains intermediate, you want to express it in a different expression. Okay, so as we know, B is an intermediate and we don't contain B in our rate law expression, so this is good. Okay, in your homework, and when you're typing the answers for the homework, do not put 1 because they did not indicate K1. Okay, you should just put K and then the concentration of A raised to the second power. Let's try another problem set where also the initial step is slower step. Again, the first step we want to do is we want to find out the intermediates from this reaction. So I'm going to add up all the reactants.
Professor, I'm sorry to bother you.
Yeah.
So on the previous question, how come we only found the rate law for step 1, but not step 2?
Because so I want you guys to memorize this sentence. The rate determining steps governed the rate law for the overall reaction. What is a rate determining step? Rate determining step is a slow step. Okay? So if you see a slow step and fast step in this reaction, multi-step reaction, you should immediately recognize that the slow step is the rate determining step, and that slow step will govern the rate law for the overall reaction.
Okay, that makes sense now. Thank
Okay.
you.
Okay. All right. So I was finding the intermediate for the reaction. I added all the reactants and I'm going to add the products. As I can see here, this I know the C is showing up on both reactant and product side, so C is an intermediate.
Really?
Oh yes.
Okay, so you know how you got the rate law for the first mechanism,
Oh, you're breaking. Your voice is breaking. I can't hear anything.
but you can't hear me.
Is it me or you? Okay. Okay. Do you want to type out your question?
Can you hear me now?
No, I can't hear anything from you.
Okay.
You might want to type out your question and I'll come back to you. Okay? So we know the C is an intermediate. Now again, if you want to find the overall rate law, we know that the slow reaction is going to govern the overall rate law of the reaction. Okay? So rate law from the slow reaction or step 1 reaction is going to be, no, wait, this one. This is the overall reaction. Okay. And then the rate law is going to be from the step 1 or slow reaction, which is going to be rate constant multiplied by concentration of A, concentration of B. Okay. Pretty simple. So when initial step is slow step, everything is pretty simple. Okay, as you can see here. But when first step is fast and when second step is slow, the situation gets a little more complicated. And this is what you guys were having trouble last week. Okay, so I'm going to go over this step by step. Again, the first thing we want to do is we want to find out. Oh, let me go back to the question. Yeah, if you want, you can type out the question. I'll come back to you. Okay. All right. So the first thing I'm going to do is I'm going to find out what the intermediate for this reaction is. Okay. So I'm going to add up all the reactants, and then I'm going to add up all the products. Okay. As you can see, C is appearing on both sides, so we know that C is an intermediate. Okay. And then, because rate law is governed by slow reaction, we know that the rate law, the overall rate law, is going to be, I need to label this. K1, K negative 1, and this is K2. Okay. So the overall rate law is going to be rate law from step 2 or rate law from slow reaction. Okay, overall rate law is going to be rate constant from step 2. This 2 indicates This number 2 indicates rate constant from step 2 of the reaction. Okay, so rate constant 2 multiplied by concentration of C, concentration of D. Okay, so this is the overall rate law. Overall reactions rate law. But what do you see here? You see this overall rate law involves an intermediate. As I mentioned from last week, we don't want intermediate in the rate law expression. Okay, the reason is because I've already discussed before, but because intermediate is unstable, it is often low in concentration, so we don't want to have this unstable concentration in the rate law expression. Okay, so I'm going to write a note here. C is an intermediate. We don't want this in the rate law. Okay, so we're going to find an alternative way to express concentration C. Okay, so let's find alternative way to find or to express concentration C. Okay, so from step 1, we know that rate of the forward reaction equals rate of the reverse reaction because they're in equilibrium. Okay, so then what we know is that rate of the forward reaction is rate constant K1 times concentration of A equals to rate of the reverse reaction is K, rate constant of the reverse reaction, times concentration of B, concentration of C. We know they equal to each other, okay? So if we find oops. So then the C is going to be K1 concentration A divided by K negative 1 concentration B, right? What we're going to do is we're going to plug this into here. Okay? Is everybody following? Am I going too fast?
It's a little fast.
I'm going a little fast? Okay.
Yeah, if you can slow down a little,
Yeah.
Dr. Lee.
Okay. All right.
You hear me now?
Okay. So I'm going to explain this one more time. So from step 1, here, we are already provided the information that this is an equilibrium reaction. That means the rate of the forward reaction this forward reaction equals to the rate of the reverse reaction. Okay? Forward reaction has a rate constant of K1. Reverse reaction has a rate constant of K negative 1. Okay? The rate equals because they are in equilibrium. Okay? Rate 1, rate of the forward reaction is going to be rate constant multiplied by this concentration. Rate of the reverse reaction is going to be rate constant of this reaction multiplied by concentration of these. Okay, so then we have this expression. So if we solve for C, we will have K1 concentration A divided by K -1 concentration B. Is that clear? And now that we have some other expression for C, we're going to plug this. We're going to plug this into here. Okay. The whole purpose was to eliminate C because C is an intermediate. We don't want this in rate law. We don't want to see C in the rate law expression. Okay. So I'm going to plug in C into the overall rate law that we wrote in the beginning. Okay. If we plug in C, this is what we're going to have. So overall rate law equals to, I'm going to rewrite this, K2 C, concentration of C, concentration of D. We're going to keep the K2. Now, concentration of C is equal to K1 concentration of A, K -1 concentration of B times D. I just substituted this with this. Okay. Then what we can do is we can do a little bit of rearrangement. Okay. All these K equals to K without any label because this rate constant is for the overall rate, overall reaction rate constant. Okay. K2 is for step 2. K1 is for reaction for step 1. K -1 is reverse reaction for step 1. But for overall reaction, you are going to have combined rate constant, and that's labeled as K, not capital letter, small k. Okay? So that's K, and then what do you have left? You have concentration of A, concentration of D, divided by concentration of B. So this is going to be the overall rate law. Okay? So basically, the overall rate law should be this, but because we don't want C, we were on a long journey to find different expression for C, and we have arrived at this. So in your homework answer key, you want to type in this answer.
I'm sorry, Dr. Lee. Could you go back to what happens to K?
What happens to this K? K here?
Yes.
Okay. All right. I'm going to explain one more time. So K2 is rate constant for step 2. You got that right? K1 is rate constant for reaction step 1. K -1 is reverse reaction for step 1. If you combine all these together, you will have a rate constant K without any subscript. This is a combined this is a combined rate constant. Okay, so the combined rate constant is K2 multiplied by 4 reaction of step 4 reaction constant of step 1, reverse reaction rate constant of step 1. This is the combined rate constant. Okay, so for overall reaction, you want to have combined rate constant. Is that clear?
Yes, thank you.
Okay, all right, let's try another example. Again, you have a slow second step. So the initial step is fast. Again, when initial step is fast, when second step is slow, situation gets a little more complicated. Okay? First thing first, let's find the intermediate for this reaction first. We're going to add all the reactants to A. 2A plus B plus C equals to B plus D. Okay? B appears on both sides, so we know that B is an intermediate. Okay? So the overall reaction is 2A plus C equals D. See, overall reaction. All right. So overall rate law equals to what? Slow reaction, right? Which is step 2. Why? Because slow reaction is a rate determining step. Rate determining step governs the overall reaction rate law. Okay? So we're going to write the rate law based on this slow equation. Slow reaction mechanism. Okay? So using step 2 reaction, the rate law is going to be K2. 2 indicates step 2. Okay? That's all it's indicating. I'm just labeling. So rate constant K2 times concentration of B times concentration of C. Okay? What do we see here? B. B is an intermediate. Again, we don't want to see an intermediate in the rate law expression. So we need different expression for B. Okay? So let's find different expression for B. From step 1, they already told us that these two the reaction is in equilibrium. So from step 1, we know that the rate of 4 reaction equals to the rate of the reverse reaction. Okay? That means rate law for the 4 reaction is going to be rate constant for the 4 reaction multiplied by concentration of A to the power of 2, because you have 2 mole of A. Rate law for the reverse reaction is going to be rate constant of reverse reaction multiplied by concentration of B. Okay? So now, can you solve for B? Yes. So now concentration of B is basically going to be this divided by this. So K1 concentration of A to the power of 2 divided by K negative 1. We're going to plug this into here because we don't want to see this in the overall rate law expression. Okay, so then if we plug that in, overall rate law is going to be K2. I'm just rewriting this. And now that we have different expression for B, I'm going to plug that in. K2 equals to K1 concentration of A to the power of 2 divided by K negative 1. Okay. I just put these on one side so that it's easier for you to visualize. Okay. This is rate constant for overall reaction. So you write rate constant for overall reaction without any subscript. You rewrite whatever we have here. So this is going to be the answer for this, the rate law for the overall rate law for this multi-step reaction.
That reaction give us a molecular reaction?
What's that again?
Would that reaction give us a thermomolecular reaction because there's essentially three parts, three exponents?
Sorry, you are breaking. Can you repeat it one more time, please?
Would that reaction give us a thermomolecular reaction?
Thermomolecular reaction. No, because this is a multi-step reaction where you have two different elementary steps, right?
Okay.
Yeah. So this is totally different from what we discussed in the earlier in the chapter 14. Okay. So yeah. So this is one elementary step. This is one elementary step. The overall reaction requires multi-step, and each individual step is an elementary step, if that makes sense. Okay. All right. Last problem. Consider the mechanism. So again, you have multi-step reaction where each step is an elementary reaction. Okay. And then they're asking you to find an intermediate and find a catalyst. Okay. So in order to find intermediate and catalyst, we have to add up all the reactants, add up all the products, see which one appears on both sides. Okay, so let's do that first. So I'm going to add all the reactants. Okay. We can see that AB is appearing on both sides. And we can see that A is also appearing on both sides. Okay? But how do you know which one is an intermediate, which one is catalyst? If you go back to chapter 14 lecture slide, it says on there that intermediate is being produced in the reaction and consumed in the reaction. Okay? Catalyst, on the other end, is consumed in the reaction and produced back after the reaction. So those are the differences. Okay? So intermediate is produced and then consumed. Okay, catalyst, you consume first and then it gets produced again at the end as in the original form, because catalyst is not consumed in the reaction. Okay, so let's see which one gets produced and consumed. As you can see from step 1, we did not have AB in the beginning. Okay, we generated AB and then we consumed AB in the step 2. Okay, so then AB is an intermediate. On the other end, let's take a look at A. We had A in the reaction mixture to start off. Okay, so we know that A is consumed first and then it's regenerated or produced back later. Okay, so then, oops, we know that A is going to be the catalyst. Okay, so these are major difference between intermediate and catalyst. They will both, if you do add up all the reactant side and add up all the product side, the intermediate and catalyst will both appear on both sides of the equation. However, the difference is that intermediate is produced first and then consumed. For catalyst, you consume it first and then it gets reproduced after. Okay, because if you look at the chapter 14 lecture note about catalyst, catalyst should be regenerated in its original form once the reaction is finished. Okay, because catalyst is not consumed in the reaction. Okay, so that's that for few of the homework problems. Make sure you guys finish your homework before the due date, which is this Sunday, 11:59 p.m. Okay. If you have any further questions, please schedule an office hour with me. We're running out of time, so let's quickly move on to chapter 15. All right. So in chapter 14, we have encountered a case where faster first step and of a multi-step reaction to be equilibrium reaction, the example that we just observed in the homework problem, right? So when a reaction is in equilibrium, this means that the reaction is in a state of balance. So during this state, the forward reaction and reverse reaction take place at the same rate. Okay? The forward reaction and the reverse reaction, they take place at the same rate. So no net change occurs. This is called equilibrium, and in this chapter, in this entire chapter 15, we will thoroughly study about that chemical equilibrium. Okay? So the picture here is showing frozen N2O4 in a sealed glass tube. Okay? Dinitrogen tetraoxide in a sealed glass tube. This solid has a boiling point of 21.2 degrees Celsius, and as the glass tube is heated, dinitrogen tetraoxygen boils and it becomes gas and forms the nitrogen dioxide gas. Okay, a light brown color here indicates the presence of nitrogen dioxide, and as the sample is further heated, okay, more and more nitrogen dioxide is going to be generated, and the tube has darker brown color. Okay, but the tube does not get any darker because equilibrium is reached, where we have equilibrium mixture of dinitrogen tetraoxide and nitrogen dioxide in the tube. So once the equilibrium is reached, even if you leave this, because the equilibrium is reached, even if you leave this tube overnight, no further nitrogen dioxide is going to be generated. So the color will remain dark brown. It will not get any darker because no more NO2 is going to be generated. Okay. So here's a diagram showing the concentration of dinitrogen tetroxide and nitrogen dioxide over time during the reaction. Okay, let's focus on diagram A. The diagram A is showing the initial concentration of dinitrogen tetroxide N2O4 being higher. Okay, it's starting at higher concentration and it decreases as the NO2 is generated. Okay, the orange line is the concentration. The orange line here is the concentration of NO2, and as you can see, the initial concentration of NO2 is 0. Okay, it's at 0 because you don't have NO2 in the beginning. But as NO2 gets decomposed into as N2O4 decomposes into NO2, the NO2 concentration increases. Okay, that's what this diagram is showing. Diagram B is showing the reaction rate. Over time. This is concentration over time, but this is showing rate over time. Okay, F here indicates forward reaction. R here indicates reverse reaction. Okay, rate constant, Kf is the rate constant for the forward reaction, and then Kr is going to be the rate constant okay. Kf is going to be the rate constant for forward reaction, and Kr is going to be the rate constant for the reverse reaction. And as you can see, this is the rate law for the forward reaction, and this is the rate law for the reverse reaction. And as you can see, as time goes by, once equilibrium is reached, rate of the forward reaction equals the rate of the reverse reaction. Okay. So in a system of dynamic equilibrium, although reactant and product concentration remains the same, okay, no net change of the concentration of reactant and product is observed. It will remain the same, but that doesn't mean that they stopped reacting. The reactants and products are constantly being made at the same time. And that's why it's called dynamic, because the system is constantly in action. Okay? So for dynamic equilibrium to occur, neither reactant nor product can escape the system. Okay? That's the condition. The concentration of product divided by concentration of reactant will equal to a constant, and we will investigate more about this detail about this constant in next few slides. So again, this slide is basically telling us that although reactant and product concentration remains the same, that doesn't mean they stop reacting. Okay, the system is in constant action. The reaction from reactant side, the reaction from product side is constantly going on, and that's why it's called dynamic equilibrium. Okay, that's why it's called dynamic. All right, so let's thoroughly study about this equilibrium reaction between N2O4 and NO2. Okay. Make sure not to forget to use the double arrow when you're expressing an equilibrium reaction. Okay. All right. So we have this. The 4 reaction is going to be N2O4 producing NO2. Okay. We are using one arrow because this is showing the 4 reaction only. Okay. The rate law from this equation is going to be rate constant for 4 reaction multiplied by concentration of the reactant. Okay, so that's going to be the rate of the 4 reaction. For reverse reaction is this part of the reaction, right? For the reverse reaction, we have NO2 producing N2O4. Okay, so then the rate law for the reverse reaction is going to be rate constant of reverse reaction multiplied by NO2 concentration to the power of 2 because you have 2 mole of the NO2. Okay?
Professor Lee,
Mm-hmm.
on an exam, are you going to want us to put KF or KR depending on if it's forward or reverse?
So it's going to be multiple choice. So yeah, it doesn't really matter what you label because I'm not going to be able to see what you wrote. This portion is this, and then this portion is this, and then this portion is this. Okay, rate of the 4 reaction equals to rate of the reverse reaction. Okay, so okay, and if we rearrange this equation so that we have rate constants on one side, so that we have rate constants on one side and then the concentrations on one side, we're putting KF over KR here, here, okay, and then we're putting these two concentration factors here. Okay, so if we do that, if we divide rate constant of 4 reaction by rate constant of reverse reaction, we will get a constant. And this constant is capital letter K equilibrium. So rate constant, capital letter K EQ is constant rate the equilibrium rate constant. Okay? Okay, so equilibrium rate constant has a formula of rate constant of the forward reaction divided by rate constant of reverse reaction, or you can also use concentrations of the product and reactants to find the equilibrium constant as well. Okay, so and one thing you need to note and keep in mind, this is a little confusing. So note that if you look at the concentration, this is a concentration. Let me bring this equation down here. As you can see, this is a concentration of product. Okay, and this is a concentration of reactant. Okay, so always make sure the numerator should be the concentration of product, denominator should be the concentration of reactant. But when you're expressing in terms of rate constant, rate of the forward reaction constant, rate constant for the forward reaction is going to be on the numerator. Rate constant of the reverse reaction is going to be the denominator. Okay, so I know that the product is related to the reverse reaction. Reactant is related to the forward reaction, but because we arrive at this ratio from this equilibrium expression, you need to keep in mind that when you're expressing a equilibrium constant in terms of concentration, product is going to be on the numerator, reactant is going to be on the denominator. If you're expressing equilibrium constant using the rate constant for forward reaction, reverse reaction, forward reaction is going to be in the numerator, reverse reaction is going to be in the denominator. If you don't want to memorize this, this is what you have to memorize. Because you can always deduce this from this expression. So the Haber process is the industrial preparation of ammonia from nitrogen and hydrogen. Okay, this process is important and critical for fertilizers production. This Haber reaction is known to be an equilibrium reaction in the closed system. Okay, and since equilibrium constant, so another way to label KEQ is KC, rate constant. Okay, they're the same thing. So since the equilibrium constant is product concentration over reactant concentration, the equilibrium constant for Haber process will have such an equation. Okay, concentration of product, concentration of reactants. Okay, and now you have to pay special attention to the powers. Okay, the powers for the product concentration and reactant concentration is going to be equal to its coefficient in the balanced equation. Okay, so NH3 concentration is raised to the power of 2 because it has coefficient of 2. H2 is raised to the third power because it has coefficient of 3. Okay? Continue with the Haber process. this diagram shows how the concentration of hydrogen, nitrogen, and ammonium vary with time. Okay, this diagram on the left is representing a forward reaction. Okay, and here, as you can see, the concentration of the reactants, nitrogen and hydrogen, are higher, and concentration of product, the ammonium, is 0 to start. And as the reaction progresses, you see that the equilibrium is achieved, and all the hydrogen, nitrogen, ammonium will reach certain concentration, and there's no fluctuation in the concentration. Diagram on the right is a diagram of reverse reaction. Okay, and then here we see that if we're going from ammonium to decomposition of and generating N2 and H2. In here, we see that concentration of NH3 is higher, and then concentration of N2 and H2 are 0 to start. And as the reaction progresses, the equilibrium is reached, and you see that hydrogen, ammonium, nitrogen, they all reach certain concentrations. And it's interesting to see that, notice that equilibrium mixture is obtained regardless we begin it with N2 and H2, or if we begin in H3. The equilibrium mixture is obtained regardless whether we go from forward reaction or we go from reverse reaction. So, and once the equilibrium is reached, the concentration of these three substances are same, whether you start reaction from forward side or reverse side. The concentration are same. Okay. So now let's take a deeper look at the equation for the equilibrium constant C. Okay. So here's a general formula of how to find equilibrium constant Kc. Okay. So Kc stands for equilibrium constant. Okay. Numerator is going to be multiplication of concentration of all substances on the product side, each raised to a power equal to its coefficients in the balance equation. Okay. Oops. Okay. It's each raised to a power equal to its coefficients in the balance equation. Okay. Denominator is going to be multiplication of all the concentration of substance on the reactant side, each raised to a power equal to its coefficients in the balance equation. Okay. Each raised to a power equal to the coefficient in the balance equation. Okay. All right. So now let's do a practice exercise. We know the general formula how to find Kc. So let's find the equilibrium constant for reaction A. Okay. So the Kc is going to be the numerator is going to be the product concentration, each raised to power equal to its coefficient. Product is O2 raised to third power, divided by denominator is reactant concentration raised to the power equal to the coefficient. So that the equilibrium constant for reaction A is going to be like so. For B, Kc is product's NaCl raised to the power equal to the coefficient divided by reactant each raised to a power equal to its coefficient. So it's going to be this. For C, AC is going to be product raised to the power equal to the coefficient. Coefficient is 1. It has nothing, so I'm not going to put anything. Divided by reactants concentration raised to the power equal to the coefficient. Silver plus Ag plus has 1, so I'm not going to put anything. Ammonium has a coefficient of 2, so I'm going to raise to the second power. So that's going to be the Kc for reaction C. Okay, let me know if I'm going too fast or if I'm scrolling too fast, okay? All right.
Professor?
Yeah, you want me to go back?
No, I was just wondering, yeah, if we could just slow down just a little bit. I'm sorry, I just don't have time to write the question.
Yeah. Okay, take your time.
Sorry, thank you.
Let me know when you're done, okay?
Okay, I'm
Okay.
done, thank you.
All right. So when the reactants and products in chemical reactions are in gas state, we can also formulate the equilibrium constant expression in terms of partial pressures. Okay. Express or formulate equilibrium constant in terms of partial pressure. Okay, so when partial pressures in ATM or atmospheric pressure is used in the expression, we denote the equilibrium constant Kp, okay, instead of Kc. P stands for pressure, okay? So this Kp is the equilibrium constant in terms of pressure, okay? And then P is going to be partial pressure of A, and the unit is normally ATM, atmospheric pressure, okay? Partial pressure of A or B or C. So PD is partial pressure of compound D. We're working with this equation, by the way. Okay, so partial PD is going to be partial pressure of compound D. PE is going to be partial pressure of compound E. PA is going to be partial pressure of compound A. PB is going to be partial pressure of compound B. A, B, C, D. These are the coefficients, and as very similar to Kc, each of the partial pressure is going to be raised to the coefficients in the balance equation, raised to the power of equal to the coefficients in the balance equation as well. Okay, so let's take a look at an example. Let's say you're working with reaction N2O4. You're working with this example, for example. If they're both gas state, you can also express Kc in terms of Kp, okay? Because this involves pressure, okay? So then the Kp is going to be partial pressure of NO2 raised to the second power divided by partial pressure of N2O4 reactant raised to the power equal to the coefficient. Coefficient is 1, so I'm not going to put anything there. Okay, so yeah, this is Kp. One thing you have to note is that the numerical value of Kp is going to be different from Kc. Okay?
Professor Lee.
Yeah.
Does KP and KC have any units that we need to know?
Okay, that's a good question. So technically, they will have unit. However, by definition, the equilibrium constant, they're considered as constants, so they will be reported without units. Okay, so we are not going to worry about units for these equilibrium Kc and Kp in this chapter 15. Okay, very good question.
All right, thank you.
Yeah. Mhm. All right. So yep, Kp and Kc, if you ever have to report the rate constant, equilibrium constant values, they should be reported without a unit by definition, okay? All right. So as I said, Kp and Kc, they will have different numerical values, but we can calculate one from the other using the ideal gas equation, okay? So let's say if we know Kc, the question might ask you to find out what Kp value is. If the question is it's provided with the Kp information, the question might ask you to find Kc, okay? That relationship we're going to investigate in the next few slides, okay? So first thing first, the ideal gas law states that PV equals nRT. I'm pretty sure you guys are familiar with this equation. This is the ideal gas law. If we rearrange this, we're going to get this. So if we rearrange this equation and express it in terms of P, pressure, we have, and this is basically N over V times RT. Okay? This N over V is basically mole per liter. Okay? Because N has a unit of mole, volume has a unit of liter. Okay? So it's basically mole per liter. So it equals to molarity. Okay? So this portion is basically, let's say you're working with compound A, it's basically concentration of A. Okay? So if you are expressing partial pressure of compound A, for example, partial pressure of compound A is basically concentration of A times RT. Okay? R is the gas constant, temperature is going to be the pressure. Okay. Oops. We derived this equation from the ideal gas law. And this will allow us to arrive at this equation. And this shows the relationship between Kp and Kc. So if we are provided with Kc information, you should be able to find Kp. If we are provided with the Kp information, we should be able to find Kc. Next slide, I am going to show you how we arrived from here to here. Okay, I'm running out of time, and this rearranging of math takes a long time, so I'm going to continue that in next class. Okay, so as of now, just know that Kp is different from Kc. The numerical values are different, but if you know one value, you can find the other value. And next class, I'm going to show you the process of how we arrived to this equation, okay, which shows relationship between Kp and Kc. That's it for today's class. I'm going to stay for another 5 to 10 minutes just in case anybody have questions. If you don't have any questions, feel free to leave. I'll see you guys again next Tuesday. Okay.
I just wanted to say thank you for going a whole lot slower this lecture. That helped.
Yeah.
That
Okay.
helped me. Thank
Yeah,
you.
I'll try to go slower.